Okay, yeah, so we're on to lecture 3. So last time we were in the middle of a calculation of the QQ bar gluon, the real emission diagram, or diagrams for that, as written there. So those two there. And remember, we were talking about the color factors and how you calculate them and so on. And I skipped a few steps because it's, it doesn't gain much going through all of the kind of gritty detail of the calculation, but in the end, from those traces over the momenta, you get this thing here, where again, I use this notation a lot, which is this Sij, which is just the dot product of the two momenta as labeled by I and J. Again, A and B are the incoming electron, positron momenta, and then we've got 1, 2, and 3 labeling the quark, antiquark, and the gluon. So we're not quite there yet, because what I've written here is an expression for the matrix element squared, so it's suitably kind of averaged and summed and so on. But we want the cross section. So the next step is to get the cross section. And there are a few steps here. It's a 3-body phase space, so it's not completely trivial at all. Even at that level, you can sort of do things analytically for the 2-body case. You can also do it here, but it becomes rather more complicated. So I'm not going to go through again every detail, but so what we want is, okay, 1 over 2s, a 3-body phase space. Let me write it like that. And a quark, antiquark, gluon. That's what I've just shown before, and where I'm defining in my other notation S just to be SAB, because that appears a lot. So that's just the squared center of mass energy. So and here, right, this thing here, this D phase space 3 is equal to 1 over, you've got various factors of pi, and you've got an integral over the 4 momenta of the 3 particles, the quark, the antiquark, and the gluon. And they all have to be on shell and massless. Remember, we're neglecting quark masses here. And we've got an overall delta function giving you energy momentum conservation, right? And so that's it. And then the rest is sort of manipulating that, essentially. So the various steps to doing that, but in brief. So step 1 would be to eliminate, just to kind of give you an idea of how this would work, is to eliminate the D4P3 with just the delta of 4, so that just hits that and that goes straight away once we integrate over this. Indeed, just putting an integral like that, just to be clear. And so yes, D phase space 3 then goes to 1 over 2 pi to the 5, D4P1, 1, D4P2, and we've got those 3 delta functions, the on shellness, but also for the third gluon. And then step 2 would be to do this. Again, hopefully straightforward enough. One can do a little bit of manipulations. First of all, one can get rid of the delta functions, right? This is just in terms of the 3 momentum. So implicitly, the energy is then obeying the usual E squared equals P squared plus M squared relation. And so you get this. You can write that just as well as an integral over the energy in that case. So that's what we generically do. So there it is. Okay, the fact that it's a 2 or something else is not too important here, but the point is that one has an integral over the energy and then over the 2 angles, the azimuthal and the theta angle of the momenta of the particle. And similarly for P2, I won't write that explicitly. Okay, so step 3 is to define this thing. Let's define an energy fraction. So I'm going to say via EI, so the energy I, 1, 2, or 3, that is equal to XI root S over 2. Okay, so EA and EB are then, in other words, just root S over 2 in the usual way. Remember that. And we can then just write the energy integral in terms of that. Okay, integral over this momentum, this energy fraction X. It's just a way of writing things in a sort of compact way. And I'll show why I've expressed things in terms of that in a minute. And finally, okay, we've got one delta 3. We've got rid of both of those, right, by writing things in this way, but we've still got that one. So we also need to eliminate that.
So we eliminate one of our angular integrals. We've got 4 of them, 2 phi's and 2 cos thetas. So we can eliminate one angular integration with the delta of P3 squared. And so something like this, a little bit schematic, but we're going to have something like that, okay, over the quark and the anti-quark. And that's just going to become that sort of thing. Okay, it doesn't really matter. I'm not never going to use those, write that again. I'm not going to actually do this integral, but just to say that one can write it in that way. And so the bottom line is that, when the dust settles, this thing looks like an integral over x1 and x2 and some angular integration as I've written it above. And one can then just trust that basically one can do the angular integration, but we won't ever actually do it explicitly. And so that's it. But let me do a little bit more, because I've defined these x1s and x2s, but if we go back to, where's it gone? To this thing here, I've written things in terms instead of these s's, in terms of these s's. So let me, for example, focus on the denominator there, and say a bit about that. So recall, let's say like this. So now recall that the denominator of mqqq bar gluon is equal to s1 3 s2 3 and e.g. s1 3 is equal to 2 e1 e3 minus 2 p1 dot p3, okay, but p1 plus p2 plus p3 is 0, right? If you just think about the kinematics of this, we've got PA and PB coming in, and the other 3 then just have to balance. Call that P1, P2, P3, say, something like that. And therefore, P2 is equal to minus P1 minus P3, and therefore P2 squared, which equals E2 squared, okay, is equal to P1 squared, so that's E1 squared, plus P3 squared, that's E3 squared, plus 2 P1 dot P3. Okay, so we can use that to rearrange and get rid of the P1, P3. And when the dust settles, so I won't do the final bits, but just to give you an idea of where this kind of stuff comes from, one ends up with S13 is equal to S1 minus X2. Okay, so if you're, it's just a few steps to go from there to there, so definitely recommend doing that. But hopefully you've got the idea of where it's going. In fact, I've given you all the elements you need, along with, let me say that one also makes use of this as well. That's where the S comes in. Okay. So when the dust really settles, so we finally get, I've given you a few of the elements of how you get there, but not all of them, of course. But you end up with this. So this stuff we've had before, there's the color factor again. Got an alpha S over 2 pi, because we've got the first order QCD correction, the gluon coupling squared. And with a little bit of thought, you can convince yourself that the actual ranges on these things go from like so. So x1 can go from 0 to 1, but x2 then is limited in that way to keep kind of a sort of a maximum energy that things can carry, given the original input root S. And the rest looks like this. So I just showed you very briefly why you got the 1 minus x2. You also get a 1 minus x1. And when the dust settles, the numerator looks like x1 squared plus x2 squared. Again, I've done the angular integration. So, that gives you factors of pi and so on, which is certainly not obvious just by looking at the expression.
Okay, so perform. So do we just perform dx1, dx2, and job done, or alternatively, express it differentially in it, or what? Is that it? Just do the integral, stick it on a computer, whatever. Well, no. If we try that, we very quickly run into trouble. And the point is that we observe this integral it diverges. And it diverges as x1 or 2 go to 1, precisely because of that numerator there. Okay. So what's going on? Suddenly the expression we've written down is not giving a well-defined result. What is going on? Well, if we want to understand what's going on, I've written down a sort of formal looking expression in terms of these variables x1 and x2, but clearly the x1, x2 goes to 1 limit should have some sort of interpretation in terms of the actual momenta of the quarks and the gluons, and sure enough it does. So that's where what we want to ask. So that's our first natural question, right? Which is, what does x1, 2 goes to 1 mean in terms of our base space? So let's do it bit by bit. So first of all, let's say x2 goes to 1. Remember, x2 is the momentum fraction of the antiquark, according to our momenta definition, as defined down there. So yeah, indeed, therefore, E2 goes to root S over 2. Okay, straightforward enough. So how are we going to get that? How is the antiquark going to carry root S over 2 energy? Let's draw that. So there's our antiquark with energy going to root S over 2. Well, if we had a 2 to 2 scattering, if we had a 2-body scattering of massless particles, that's precisely what we would have, right? The 2 particles coming in have root S over 2 energy, and the 2 particles coming out, therefore, will also have root S over 2 energy. So the kinematics is starting to look rather 2-body-like. And indeed, the only way you can get this to happen, to be allowed by momentum conservation, is if the quark then and the gluon actually go in exactly the same direction. So completely collinear, balancing the antiquark. So indeed, it does start to look precisely 2-body-like. So let me draw that, sort of like that. And there they're going in that direction. And that then is my quark and my gluon. And we can write that the quark is collinear to the gluon in that sort of brief notation. So indeed, the kinematics are 2-body-like. And this is only allowed if the recoiling P1 and P3, it's the quark and the gluon, are going in the same direction, which is in the opposite direction then of the antiquark. I.e., the quark is, we say, collinear to the gluon, or the gluon is collinear to the quark. And it's no surprise then that for the x1 goes to 1 limit, it's now E1 goes to root S over 2, and it's just going to be the same, but now we're quark swapped to antiquark. So now the quark there, x1 goes to 1, so it's E root S over 2, oops, and the antiquark and the gluon collinear. Okay.
because I've not drawn them exactly going in the same direction, because just to show what's there, but you know, that's kind of implied, if you like. So now the antiquark and the gluon must be collinear. So finally, though, there is one final thing, which is finally, what if both x1 and x2 go to 1? So at the moment, I've just said one of them individually. Is there a way we can allow both of them to go to 1? There is. So if both x1 and x2 go to 1, then now the quark and the antiquark really are just back to back with root s over 2, just like in a two-body scatter. And so the only way that can happen is if the gluon's energy goes to 0. Okay? So then the quark and the antiquark are back to back with root s over 2. And therefore, the energy of the gluon has to go to 0 for that to happen. So we've got a soft gluon, as we say, being emitted. So let me draw that. Well, I don't know, one could draw it like this, quark and an antiquark. Oops. Quark and an antiquark, and maybe slightly schematically, just draw a little gluon like that, so a soft gluon being emitted. The angle of it doesn't matter, it's just that the energy has to become, you know, goes to 0 in that limit to allow this to happen. Okay, so that's where we expect this to happen. So why is it happening? And when I say why, I mean, well, fundamentally all I've done here is calculate something from a Feynman diagram. So one should be able to point to something in the Feynman diagram and say, this is why it's happening. And indeed you can. So let's do that. So in terms of Feynman diagrams, where is this coming from? So let's think about, just do one example. X2 goes to 1. And let me draw a Feynman diagram. So there's our Feynman diagram. And this is the one we're actually interested in, as you'll see in a second. So that's P1, that's P2, that's P3. Therefore, that is P1 plus P3. Okay. So this thing here, the amplitude goes like P1 plus P3 all squared, of course, plus a lot of other stuff, but that's the thing we're interested in here. Now, P1 plus P3 all squared equals simply 2P1, P3, because these things are on shell and massless. And that's equal to 2 E1, E3 to 1 minus cos theta 1, 3. Okay. So now recall, right, if I go back to here, so x2 goes to 1, we thought kinematically that was with the quark and the gluons at P1 and P3 going in the same direction. Okay, and you can see this propagator depends on precisely those momenta and indeed on their angle, as I've just expressed it. So P1 collinear to P3 implies that cos theta 1, 3 goes to 0. Okay, straightforward enough, i.e. cos, of course, cos theta 1, 3 goes to 1. And so S13, which again, as I've just written it, is this, goes to 0. Then we look back at the Feynman diagram and it's precisely a propagator, 1 over that thing, which is there. And therefore, you know, this thing is like 1 over 0, if you like, it's diverging. And that is nothing other than the 1 over 1 minus x thing that we saw there. That's all it is.
that's where it's coming from. So indeed, this is precisely what we saw in the original expression for sigma q bar. Oops. Sigma q bar gluon. So a bit more precisely, okay, 1/0 isn't a great thing to deal with. So let's just say it's small. So theta 1, 3 is small. And we can just Taylor expand cos theta. So let's do that. And so this is what we have actually. E1, E3, cos theta 1, 3 squared, which clearly, as I claimed above, goes to 0 when the angle goes to 0. And so 1/P1 plus P3 all squared goes like, when the gluon becomes collinear to the quark, 1/E1 E3 theta 1, 3 squared. And indeed, you know, that goes off to infinity. Theta 1, 3 goes to 0, just to restate the point. And yeah, similarly, one can do it with the other diagram for x1 goes to 1. And that would be theta 2, 3 going to 0. The other thing to say is that one can see that E3 is here in the denominator in both of those cases, in fact, and therefore also clearly S13 as defined above also goes to 0 as E3 goes to 0. So that's our soft gluon. So that's also there. Okay, so it's clearly there. It's clearly there in the Feynman diagrams, and it's clearly an issue, right? So the question is, how do we interpret it and how do we deal with it? So let's talk about that. So how to interpret this? So let me give a kind of heuristic argument for what the basic idea is, and then talk about the solution to it as well. So the basic idea, let's remember, is that E plus E minus to hadrons, right? We wanted to relate, put it like that, if you like, to that leading order diagram or whatever else we add in the higher order calculation. And I just sort of said, kind of by fiat almost said, well, yes, we can do that. We don't care that they hadronize in the end. We can just calculate it in terms of the E plus E minus to QQ bar diagrams, but that's definitely not obvious. And so one would need to justify that. And indeed it is justified, and one can give a kind of physical argument for why that's the case. And the argument relies on a factorization argument, essentially. It's a factorization argument between the time scale of the production of the quark and the antiquark and the time scale over which hadronization happens. So let me clarify that. So the time scale for, let's say, our off-shell photon to produce the quark antiquark, okay, after, produced on the E plus E minus, is of order 1/√S, okay? And that's just really just a sort of basic hand wavy, but certainly valid uncertainty principle argument, okay? So the energy there is of order √S going through the photon, and one expects therefore the characteristic timescale over which that formation happens to be of order 1/that. Because I'm setting h bar to 1, we always work in natural units, why it's not present, but then I've reintroduced it there to be clear that where that's coming from. And here's the thing, while the time scale for hadronization, so for those quarks and antiquarks and whatever else to actually form pions and so on and so forth, is going to be, so in other words, let me write that. To be clear, the QQ bar to hadrons or whatever else, QQ bar gluon to hadrons, etc. T hadronization, well, it's going to be of order the sort of 1 over the energy scale lambda QCD, at which QCD becomes strong. So 1 over the proton mass-ish, okay? It's the characteristic energy scale of this hadronization, the characteristic time scale as well, 1 over that. So in other words, then provided root S is a lot bigger than lambda QCD, which is certainly true, right? I mean, if root S is aboard the proton mass, we're very much in the sort of low energy resonance region. We want to be well above that, and we are. Provided that's the case, then the time scale for, let's say, the QQ bar formation, let's write it like this, to be clear, time scale for the off-shell photon to form a QQ bar is going to be a lot less than the time scale for hadronization. Okay. So this thing here, much smaller energy scale, so 1 over it's much larger. Therefore, that's what we get. Okay. And this is really the basis of the calculation. So the basis of the calculation, the basis of never worrying about that when we do this calculation, B plus E minus 2 hadrons in terms of quarks and gluons, is that hadronization happens much later than the actual formation of the quark and the antiquark, which we calculate in perturbative QCD. And therefore, we can ignore it in the total cross-section calculation. So let me draw this very schematically. And let's say we're at t equals 0, right? And then maybe our, as I say, it's a little bit schematic, but there's RE plus and RE minus coming in, annihilating. Then we go to t of order 1 over root s, approximately equal that. And now the quark and the antiquark have been formed, and that's the thing we calculate. And now here's the thing. That happens, we calculate it, and then you wait, and much later than that, t order 1 over lambda QCD this thing, these hadronize, they form pions, photons get emitted, whatever else. Okay. And so really we do have an actual separation between those two processes we expect in our calculation. So the long distance, long time scale, physics. Now, I'm not proving anything here, but I'm motivating what we want to happen. One can show it. So let me write that again. It should be independent of, let's say, or factorized from our E plus E minus to QQ bar or QQ bar gluon or whatever else calculation. Now, what's the relevance of this for these singularities I've talked about? Well, that I'll come on to now. So what about our theta 1 free goes to 0 limit? Okay, stick with that. And let me draw it again. V3, V1, V2. And again, there's the propagator in there, P1, P3. Remember, that's of order E1, E3, theta 1, 3 squared, which goes to 0. And therefore, in the theta 1, 3 goes to 0 limit, our quark propagator goes on shell. Okay. In other words, with p squared propagator, if you like, going to 0. So what does p squared equals 0 mean here? Well, that just means it's an on-shell, externally long-distance propagating particle, right? You know, an on-shell particle is just a particle, right? Something that we actually observe rather than something that exists just as a sort of intermediate field excitation. So an on-shell particle is an externally propagating state. So not a virtual thing. And so as theta 1, 3 goes to 0, propagator starts to go on shell. And quark is propagating, moving, traveling over a long distance and time scale. Okay, now we just talked about a separation of time scales. We want one thing to be short over a short time scale, the production of the QQ bar, and the hadronization to be on a longer time scale. And this is where we run into issues. So the time scale, the gluon emission is going to be of order by the same sort of arguments, something like this, very schematically. In fact, potentially, perhaps even to write it like that might even be more correct. But the relevant thing is that it goes like 1 over theta 1, 3. So smaller angle means longer time scales. And so this can be much, much greater than root S, okay? Which is what we wanted to happen. We didn't want to happen. So this precisely enters the T over 1 over lambda QCD regime we want to be insensitive to. So what is this thing telling us? It's telling us that the calculation as it stands has got real issues with it. And in particular, it's actually sensitive to long distance physics, really a regime where the binding of quarks and gluons and the hadronization of them is relevant when one is being sensitive to that. And so the calculation itself seems to have no firm foundations at all. So this indicates a sensitivity to long distance physics. And this is known because of that as an infrared divergence. Or IR. See that a lot. Now the point to make is that in reality, nothing is actually infinite. Nature, you don't have infinite observables, and nothing is infinite here. But rather, as let's say t the gluon emission goes like 1 over lambda QCD. When you enter that regime, our our perturbative QCD theory doesn't make sense. So it's just indicating that the theory is breaking down. Hence, things are blowing up. So this really seems to be a disaster. Well, in fact, as you might anticipate, that's not the case. So in fact, not so. So what's the solution? Well, certainly everything I've said is correct. That is how those real emission diagrams behave, but we haven't included everything in our calculation. That is the solution. So what have we missed? We missed our virtual corrections. Maybe you even anticipated that as I first wrote down the real corrections and I said nothing else about them. So MQQ bar virtual, to put a V to indicate that. The relevant thing actually would be something like this. We're not going to get into the details of what you include here, but we're not going to do any loop calculations or anything like that at all. That's beyond the scope, but let me draw a diagram. And this thing here has some loop momentum L, and of course this goes like you end up with an integral over it, okay, times some other stuff. And the point is that this, from a procedural point of view, without thinking about the interpretation, and this also has IR divergences. So if you consider the virtual corrections on their own, you'd have the same issue, apparent sensitivity to long distance physics. So, but now there are no external gluon momenta, it's just all internal, and it's the internal loop momentum now. Either the energy goes to 0, you get soft singularity, or the actual loop momentum, in fact, if that becomes collinear to the P1 and P2, that also gives you, in fact, an infrared divergence. And again, the reason for that is because now the propagators are there, and those are the things which can go on shell and therefore be sensitive to long distance physics. So now we remember our final state is just everything, E plus E minus to hadron. So anything that can be produced in the process, which gives you quarks, antiquarks, and gluons in the final state at the given order in alpha S you calculate, should be included. So it's just everything. So the NLO calculation is going to equal our M real plus our M virtual. Things like this, very schematic, the cartoon like that. Both have to be included. And in particular, this makes sense from the point of view of counting powers of alpha S, because we don't want to include anything beyond the order in alpha S we calculate. It's always a perturbation series. And so for the virtual one would get something like this. Okay, that'd be the amplitude, and one would multiply by the leading order amplitude star, or vice versa. And that one can see one has two couplings there, so that's clearly of order alpha S, just as and therefore it's of the same order as that sort of thing. Okay. And here's where the magic happens. What happens is that these both have individually these infrared divergences, but including everything, we actually find that the infrared divergences, singularities, it's just another word for the same thing. You might see that in the real emission. And the virtual diagrams exactly cancel. Okay, and so very schematically, something like this, the limit is the energy of the gluon in this case goes to 0, the real plus virtual equals 0, and the limit of whatever the angles, the two we considered, whichever limit you're interested in, also goes to 0. Okay. Individually, they blow up, but the sum goes to 0, goes to something finite, certainly. So the total cross section, E plus E minus to hadrons at NLO, certainly, and beyond that, one can show, is not, in the end, sensitive to long distance effects. And our factorized approach, again, our factorized approach is maintained. Now this is certainly not a coincidence. But actually a general result of a theorem, which goes under the name of the Kinoshita Lee Nauenberg. You don't actually have to remember those names. KLN, as that's always known, theorem, which is from the sort of early 60s. It's been around a while. Applies to QED as well, actually. It's all IR divergences. Singularities will cancel for suitably defined physical observables. And this thing is absolutely key. In particular in LHC physics. So, it's not enough that alpha S of mz is small, because one always has in a QCD calculation this possibility, particularly in those sort of limits, those soft and collinear limits, that one might be sensitive nonetheless to regimes where alpha S is not small. So the long distance, the non-perturbative regime. And as soon as you go into that regime, well, of course, one can build a model that accounts for it, and people do that, but one certainly can't just treat it with perturbative QCD. And so it's only for those suitably defined observables that you can really do this. Now, this is one example of it, and I'll say a little bit more in a bit about what other ones there could be, but it's certainly, there's no, some observables are what we call infrared safe, some are not, and that is a fact of life. There are only certain questions you can ask of your theory and get an answer that you can calculate perturbatively. So a bit about the practical stuff. So in practice, the real and virtual are some, as I say, are infrared finite, so they don't blow up in that region. But clearly, as we've just seen for the reveal one, and certainly for the virtual one as well, individually, they aren't. You sort of saw a flavor of that a little bit earlier, where I started writing 1 over 0, which looks a bit odd. And indeed, one wants to avoid that if you're going to do anything. So, okay, one could, in principle, work with the sum, but that's not really tractable. at all times. But in practice, you need to work with them individually. And so to do this, you've seen a little bit of this in the context of renormalization, which is a completely distinct issue to this. But just as in renormalization, we do have things which are blowing up in the intermediate steps, are becoming singular, and one therefore needs to regulate theory to deal with that. And so to do this, we must regulate our theory. Again, just as in renormalization. Now, again, as I say, the physical implications and solutions and whatnot are very different. They come from different energy regimes, but one, as I say, one from a procedural point of view actually uses the same thing, which is the so-called dimensional regularization, which I think you've seen a little bit of, but if not, it doesn't really matter. I'll say 2 words about it and then never mention it again. So the bottom line is you get something like this. This is in the printed notes. And all you really need to know is that this epsilon plays the role of a cutoff here. So if you set epsilon to 0, that goes back to the case where we don't have any regulation, we don't have any cutoff. You can see therefore that these things are blowing up individually, but precisely the way they're blowing up, if you like, cancels in that limit. Of course, there are finite bits which give an actually non-zero calculating contribution away from these limits. So I'm just writing them in that limit, in those relevant limits, a little bit schematically. So the sum gives you no, like that. Okay, so that's the kind of way you would deal with these things. Very, very brief. And so really dealing with these things, dealing with these infrared divergences is really one of the key issues. Oops. In higher order calculations. So you might have a kind of an impression when, if you work in that sort of field and you see wish lists for this and that, so next to leading order or n cubed LO, what's the bottleneck here? Well, to some extent, it is that literally just calculating for the virtual bits, these loops, is very non-trivial, but that is not the only bottleneck. This is also a bottleneck. The fact that you're actually dealing with things which along the way are blowing up, but you want in the end to be, we know in the end, have to be finite, and that can really add some complication. So in particular, maybe even just from a sort of practical point of view, we would like, if someone runs, if you run a Monte Carlo that works in next to leading order in QCD, and I've just shown you all this stuff about how, individually the real and the virtual are blowing up, but okay, if we do it all analytically and in dimensional regularization in the end and you add them all up, everything's finite. I mean, fine, but how on earth do you deal with that in a Monte Carlo? In an actual generator, some computer code, and that's clearly a question. Well, it is a solved issue at NLO, but then there's a way around it. So let me say a little bit about that. So we would like numerical Monte Carlo generator to produce finite cross sections, clearly. Not just something that a theorist writes down, but actually something you can use. And this goes under the name of an infrared subtraction. So let me say something very briefly about that. And by the way, I've just sort of slipped in and started talking about LHC physics. Well, as I promised, I mean, all of this stuff that I've introduced in the case of E plus E minus, one also produces quarks and anti-quarks and everything else at the LHC, so it all carries over. It's completely relevant. So let me go to the next page. So we write something like this. We'll be very schematic here, but just to give you a flavor of what happens. So like in an NLO cross section, perhaps in our case, it's going to be a it's going to equal the quark anti-quark gluon, sigma q bar gluon, plus, and then you're integrating over the phase space of the quark and the anti-quark, and that's the virtual. And remember, right, that those are individually. This is goes like 1 over epsilon squared. It blows up because of the loop integral. This thing here, once you do the integral over the gluon, momentum will become also blowing up like epsilon squared. And the way you round this is that you add and subtract the same thing. So you include one there and you include one there, like so. And this thing here is something that we can deal with numerically when we want to, but also analytically when we want to. So numerically in the top line, analytically in the bottom line. In particular, it sort of goes like quark, anti-quark gluon cross section in precisely those limits. And so numerically, one has something that, you know, goes like 1 over theta squared, that sort of, as we saw before, in the correct limits. And provided that's sort of up there going like 1 over theta squared and exactly matching the theta squared blowing up of the first term, everything turns out to be finite, and you just do that numerically. But then also analytically, one can just integrate this thing analytically in dimensional regularization there and get something that looks like 1 over epsilon squared, 1 over epsilon, but of course exactly matching what you have there. Okay, so that thing as well then becomes finite. And so this is all solved. That's just a very, very brief flavor of how this works. Of course, I'm skipping out a lot of the details. It's really solved and automated at NLO. And at NLO, things become more complicated, but there are different solutions on the market. But it's certainly one of the big complications. Many methods to do this on the market. Okay. So let me write that. And let me say that, you know, the fact that quark anti-quark gluon plus that give a finite result seems a little bit magical in a way. So how's it happening? And this is for arbitrary Q and Q bar phase space points, right? Or angles, really. Seems a little surprising. So is there some sort of underlying reason why this thing might happen? And indeed there is. And it hints that the soft and collinear limits should be rather special. And in particular, as I'll argue, they should have some universal behavior. But I'll deal with that in the next lecture, and stop there for now.